Okay, now let us move on to question 8. Now, for question 8, right, first let us define what is isoelectric point. So for isoelectric point, right, it must have the first keyword pH. Yes, isoelectric point is the pH where the species is another keyword sweeter ion. Okay, where you have a for the amino acid, you have for example, you have a negatively charged group and a positively charged group on the same species. Ah, okay. So therefore, because of isoelectric point, right, they already gave to you already. It is 6.1. Therefore, alanine at 6.1. Oh, sorry, there is an error right here. It's not supposed to be OH. Sorry, remove this. It's supposed to be COO minus. Okay, so now this is where you have your positively charged group and your negatively charged group together. Okay, positive charged group and your negatively charged group together. So this is what we call your sweeter ion. Okay, now let us analyze why would it form this the left and the right. pH 10, pH 2.0. This one means it is basic, got a lot of hydroxide. This one means it is acidic, got a lot of, here got a lot of OH minus, here got a lot of H plus. Okay, so because of this side got a lot of OH minus, right, the NH3 plus, right, will definitely become back NH2. Then the COO minus remains because it's under basic conditions. Whereas for alanine under acidic conditions, right, the NH3 plus remains, but the COO minus will become COOH. So that is what it means when it is at the isoelectric point, when it's either more acidic than isoelectric point, more basic than the isoelectric point. Okay. As for this, please make sure to show your peptide bond. So what I display right here, this is your peptide bond. Okay, and do take note of one thing. Please remember, must show these two. This two is very important. What are those two that I put right there? Those are your connecting bonds to other repeat units. You must show that it is part of the polypeptide still. So you must show these two connecting bonds to other repeat units. If you don't show this one is considered your -1 mark. Okay. Now, next question. Explain why condensation polymer can normally biodegrade more easily. Condensation polymer can be, first the keyword right there can be hydrolyzed. Hydrolyzed means that react with water. How come condensation polymerization can react with water? Please do not forget that condensation polymerization have either ester or amide group inside there. Both of those groups can be hydrolyzed or react with water. Whereas for this addition polymers, it only has alkyl chains, alkanes. So the alkane part cannot be hydrolyzed. Therefore, condensation polymerization is more easily biodegradable. I need to zoom in a bit. Okay, now for this particular one, okay, I don't quite like the way they do it. I like to show the full steps, so don't mind if I show you the full steps, because I don't like the way sometimes Cambridge like to take shortcut. So first thing first is I find the molar mass of ethane amide. So I get it to be 59.0 grams per mole. Okay, so then I first find the concentration of CONH2 in aqueous. Now you might ask, why do I want to find the molar mass of ethane amide? Because for concentration, right, is moles per decimeter cube. This is your mass 0.935 over 59.0 divided by 0.05. Why 0.05? 50 centimeter cube of water changed to decimeter cube, 0.0500 decimeter cube, 0.3169 moles per decimeter cube. So this one, do remember, is the concentration in water, and I want the exact amount, moles per decimeter cube. How come the mark scheme don't put divided by 59 leh? Sometimes can be like that because they're doing shortcut. I'm not showing you the full step. Okay. Now remember, there's 1 gram inside there. Whatever 1 gram left, right, if 0.935 enter into the water, the remaining of those will enter into octane 1-ol. So again, divide by 0.05 because it's 50 centimeter of octane 1-ol. So 1 minus 0.935. The mass remaining enters into octane 1-ol. Divide by 59 moles per decimeter cube, 0.0203 moles per decimeter cube. Now, then what is partition coefficient? Partition coefficient, right, is on top layer over bottom layer. Oh, by the way, there's a slight mistake here. Please ignore this. This is a mistake because it's not ethanol. It's supposed to be in octane 1-ol. This is supposed to be in octane 1-ol. Sorry, ignore this mistake. I'm not ethanol. Octane 1-ol. Okay, now, so how come the aqueous salt is top layer? Because octane 1-ol, right, is actually more dense than water. Actually, octane 1-ol is more dense than water. But how do we know that, sir? Okay, I want you guys to remember this. If they ever ask a question like this, right, calculate the partition coefficient Kpc of ethane amide, right, and they give you the two solvents, water and octane 1-ol. I want all of you to remember, first solvent is often the top layer. Second solvent after that is often the bottom layer. In case you say, do I have to memorize density like that? No need. Just remember, if they give you for the partition coefficient in the two solvents, the first solvent given will always be the top layer, the second solvent will be the bottom layer. And that's how I get it to be about 14.4. Round it up to 3 significant figures. Yeah. Okay. So this one makes sense. So you have your ethane amide 1 gram, 0.935 enter into water, the remaining enter into octane 1-ol. And all this just for 1 mark. The harder question, right, will be the next one. Okay. Sorry. Okay. This one is slightly the harder question. Now, for this particular case, I want to take note of is that you have 50 centimeter cube already contain the 0.935, then shaken with another 100 centimeter cube of pure octane 1-ol. So what is this? This is what we call this a second extraction. Okay, so that means the 0.935 already entered into the water. We take the water again and we add back octanol again. We add octanol back to the 0.935 grams of ethane amide inside that water again. We add back again octanol. We separate, extracted the second time. So this you can call it second extraction or separation again for the second time. Okay, so this one I have no choice already. So the mass of ethane amide that is dissolved inside the 100 centimeter cube, this one please remember, from water. Okay, I give it a thing, I call it, let this be X. So the concentrated ethane amide in aqueous water, right, will be 0.935 the second time we do it, 0.935 minus x, because the x amount will enter into the octanol, sorry, not ethanol, octanol, 0.935 minus x over 59 over 0.05. So I get this amount. This is so in water. Please remember that. Whereas this one is x added into octane 1 all over 59 over 0.1. This is in octane 1 all. Do take note that is 0.1. Don't use like 0.05 because now they use how many? They use 100 centimeter cube. That's why it's divided by 0.1. KBC based on the previous one is 14.38. So now I say that the KBC is the concentration of ethanamide in the top layer, water, over the concentration of CO, ethanamide in octane 1 all. I don't know why I keep it right ethanol. Octane 1 all. So I get this amount. So now, then I solve for x. What I'll get is that x will be 0.1142, 0.114. So it is 0.114 grams that enter into the octane 1 all. And that's how you get the final answer. All this for 2 marks. This is a hard question. With that being said, that is it for question 7.